Hello everyone, and welcome to this example video of variation of parameters. So in the past lecture we saw the theory behind the variation of parameters, and if you recall that our particular solution was written in terms of u1 of t, y1 of t, u2 of t, y2 of t, where y1 and y2 will come from the homogeneous part, and u1 and u2 were given by the following formulas. That is, u1 of t was determined by some integration, and there was a minus sign over here. You will have y2, you will have f and the Wronskian, and u2 of t was determined by this integration, that was y1f by the Wronskian. And if you recall, the Wronskian was just the determinant of y1, y2, y1 prime, y2 prime. All of this y1 and y2 are coming from solving the homogeneous part. So we are going to see two examples. The first one is relatively simple. Let's call this example 1, and our differential equation is y double prime minus 2y prime plus y, which is equals to 4 e to the power t. Now the first thing we need to do is that we need to find the homogeneous solution, because from there we will have our y1 and y2. So our homogeneous equation will be this, it will be y double prime minus 2y prime plus y equals to 0. This is the homogeneous equation. Now the auxiliary equation that you are already familiar with on how to solve second order homogeneous differential equations with constant coefficients. From there you can obtain an auxiliary solution, auxiliary equation, and that auxiliary equation will be just r squared minus 2r plus 1 equals to 0. This implies r minus 1 whole square equals to 0. This means r is equals to 1, but here we have a repeated root. So our complementary solution will be c1 plus t c2 e to the power r is equal, since r is equals to 1, we are not writing 1 explicitly. This will be just e to the power t. This is from your past lectures on solving second order homogeneous equations, where you have repeated characteristic roots. But now we want to find what is yp. This is the thing we need to find. So using the formulas over here, we can easily find that our f of t is just 4 e to the power t. So let me just write that for convenience. And now we are going to use the formula that is prescribed over here, u1 and u2. So for u1 we'll write, let's bring up this minus sign over here, dt. We'll have our y2 right first, and our y2 is nothing but t times e to the power t. The way to recognize y2 is as follows. If you write c1 e to the power t, and here you write c2 t e to the power t, this can be written as c1 y of t, y1, and this is c2 y2 t, right? So if you compare these two parts, this y2 is just t times e to the power t, and y1 is just e to the power t. But to evaluate this integral, we also need the Wronskian. So let's just first evaluate the Wronskian, and then we'll go on finding the full solution. So y1 will be just e to the power t, second one will be t e to the power t, y1 prime will be e to the power t, and y2 prime, that is the first derivative of this function, will be just e to the power t plus t e to the power t. This is coming from the product rule, and if you evaluate this determinant, this will turn out to be e to the power 2t. So this is our Wronskian. Now u2 will be minus dt. Our y2 was t e to the power t, and our f was 4 e to the power t, and it is divided by e to the power 2t. So this is just minus dt. There is a 4, so let's bring this 4 over here. Let me readjust the place of the minus sign. So this is this e to the power 2t will cancel out all the e to the power t's in the nominator, and you will have a t over here, and the 4 is outside, so this is just minus 4 t square by 2. Obviously there is some integration constant c prime, but let's not worry about the constants. Those constants will get soaked up in the particular solution, and all the constants that you see are determined from the boundary value problems. So since we are not considering a boundary value problems, we can just ignore it for this part. So this is t to the power t square by 2, and if you just simplify it, this will only be minus 2t squared. Similarly, u1, sorry, this is not u2, my mistake, this should be rather u1, and this is u2. u2 was dt, then we will have our y1 over here. y1 was just e to the power t, f of t was 4 e to the power t, Wronskian is e to the power 2t, and now you just have 4 dt. This is just 4t, right? So our particular solution will be u1 y1 plus u2 y2. So u1 was minus 2t squared, minus 2t squared. Let me check again just so we know. Yeah, we have done this correctly. So this is 2t squared times y1. y1 was just e to the power t, and here u2 was 4t, right? So let's write 4t, and y2 was t times e to the power t. So this will be minus 2t squared et plus 4t squared et, and this is just 2t squared et, e to the power t. So this is your particular solution, and once you know the particular solution, you can write the full solution as the complementary solution and the particular solution, like this. So the complementary solution was c1 plus t c2 e to the power t, plus the particular solution is 2t e to the power t. So this is our full solution of the differential equation that we tried to solve over here. And now we are going to see another differential equation. However, this differential equation will be a bit more complicated, and I'll just give you guys the solutions because we won't be able to solve them in terms of the auxiliary equation because it will contain functions rather than constant coefficients. Now let's move on to our example 2. And the differential equation for this example we will be considering is the following. It's written as 2t minus 1 y double prime minus 2t plus 1 y prime plus 2y is equals to 2t minus 1 whole squared e to the power minus t. Here you can see that the coefficients are not just numbers, so that's why we cannot use the auxiliary equation method to solve the homogeneous equation. So the first thing we need to do, we need to reduce it down to the standard form. So let's divide by 2t minus 1. If you do that, this will be 2t plus 1 divided by 2t minus 1 y prime plus 2 divided by 2t minus 1 y is equals to 2t minus 1 e to the power minus t. Now this is in the standard form, that is, it's in the form of y double prime p of t y prime q of t y is equals to f of t. And now we can easily identify what is our f of t. So f of t will be just 2t minus 1, and you will have e to the power minus t. This is our f of t. Now I am going to give you guys the solution, that is the solution coming from the homogeneous equation, and the complementary solution is written as c1 y1 c2 y2, where c1 and c2 are numbers, remember that, and y1 of t is a solution of that homogeneous part same as y2, and y1 of t is given by 2t plus 1. You can verify that by differentiating twice and put these things in the above differential equation, and y2 of t will be given by e to the power t. So these are given. Remember, we are not solving them, these are given to us. So using this, now our first job is to find the Wronskian. So again, the Wronskian is just y1, y2, y1 prime, y2 prime, and if you put this thing, this is 2t plus 1, this is et, this thing will be just 2, and this thing will be e to the power t, and this determinant turns out to be 2t minus 1 e to the power t. This is the Wronskian. Now we want to solve for u1 and u2. So u1 will be again minus coming outside dt y2f divided by the Wronskian. So there is dt. Our y2 is just e to the power t. Our f of t is 2t minus 1 e to the power minus t. So 2t minus 1 e to the power minus t, and the Wronskian is just 2t minus 1 e to the power t. Now if you just integrate this whole thing, there will be a minus over here, dt. This one and this term, they will cancel out, these two will cancel out, it will be e to the power minus t over here because there is a e to the power t in the denominator. And now you just integrate, and this is just e to the power minus t, right? One of the minus will come and cancel this minus sign in front, and again we are ignoring the constants. So similarly, u2 will now be dt y1 of f divided by the Wronskian, and our y1 was 2t plus 1, Wronskian was 2t minus 1, and e to the power t. This is y1, and f was 2t minus 1 e to the power minus t. So this is 2t minus 1, sorry, t over here, e to the power minus t. So if you integrate this thing, the result will be just the integration of 2t plus 1 e to the power minus 2t dt, and you can integrate it to have by doing integration by parts or whatever you want to do. It will just be e to the power minus 2t, sorry, e to the power, yeah, e to the power minus 2t over here, and there will be a t plus 1 factor, and yes, there will be a minus sign. So now you are done finding u1 and u2. So finally, so the full solution, so let me just go down a bit. The full solution will be the complementary solution and the particular solution, and we are not writing down the complementary solution again because we already know it, because yc was given by c1 y1 c2 y2, and we already know y1 and y2 from here, that is 2t plus 1 e to the power and e to the power t. So let's focus on our particular solution. The particular solution will be just the thing we evaluated over here, that is 2t plus 1 e to the power minus t minus t plus 1 e to the power minus t. And again, if you want to write down the full solution, then you will just have to add these two, that is c1 2t plus 1. I'm just, okay, let me just write, this is full solution, and this is y, the full solution, c2 e to the power t plus 2t plus 1 e to the power minus t minus t plus 1 e to the power minus t. So this is how you can use variations of parameters method to solve non-homogeneous equations. They are particularly easy to solve whenever there is a constant coefficient, but they are notoriously difficult whenever there is no constant coefficient, rather you have functions. But whenever you use the variation of parameter, it should give you some idea about the particular solution at least. That what for a particular function on the right hand side, that is for a particular f, what are the solutions that you can get. That's the idea behind this variation of parameters. So this will be it for today, and I'll see you guys on the next lecture. Thank you.